Hi, welcome. Today we are going to be talking about not just proportional relationships, but non-proportional relationships. Because for everything that is, there's also things that aren't. And so, first of all, we have already talked about tables and graphs and equations. And to look at those and just kind of do a recap, what are some things that they need to have so that it's very easy to identify whether a table is proportional, whether a graph is proportional, or whether an equation is proportional. So we're just going to write a few little things about the proportional ones, how you can identify them, and maybe even put an example there. So, for instance, with tables, for a table to be proportional, first of all relationships are equivalent. Okay. What that means is that we have multiplication or division relationships both vertically as well as horizontally. So we can multiply or divide vertically or horizontally. And that means that if we were to write them all out as rational expressions or ratios, all of our ratios would be equal. So in a table, because we do need an example, in our example, remember whatever we have here, this would be our x value, this would be our y value. If we have that, that's usually one of the clues that it is proportional, but it's not the only clue. It could have 0, 0, and then everything else not be proportional. But if we have something like this, where 1 and 2 match together, then 2 would be 4, and 3 would be 6. We can see some vertical. 1 times 2 is 2, 2 times 2 is 4. 1 times 3 is 3, 2 times 3 is 6. It works vertically, but also we do have the horizontal. If I take each of these and multiply them by a factor of 2, they all end up being the same way. Now we also have talked a little bit about the ratio of y to x. And every one of these, with the exception of 0, 0, if I write them as y to x, all of these are worth 2. So that's just a real fast, remember we talked about this kind of thing. Graphs, well, graphs are pretty easy. First of all, for a graph to work, it has to be linear. Now that was kind of a fancy word that we used. Linear meaning it's in a straight line. Which by definition lines are straight, but it is in a straight line, and it needs to contain the origin. Now, contain is a fancy word, meaning it holds it, it's part of it. Think about a container. A container has things inside of it, so it has to contain the origin. Now, it could start at the origin, or it could go through the origin, depending on our information. So, remember the origin is at the ordered pair 0, 0. So an example would be for instance, if we have a graph that is just in the first quadrant, this is our x values, these are our y values, our graph could start at 0 and go in a straight line anywhere from there. Or if we have a graph that contains the full coordinate plane, it could be a straight line that would not necessarily start at 0, but would go through 0. And so, yeah, I know it's a little crooked, but I am drawing freehand, a straight line going through the origin. Most of our data that we will have with proportional relationships will be in the first quadrant, but there are things that will be in other quadrants and things that could show up as negative values. Equations, now those are really, really awesome because when we put our equations are in a particular form. Our equations are always going to start with our y value, and then they are going to multiply, and I'm just going to use m, they're going to multiply by the x value. They're going to have a number that multiplies by the x value. What that number is the proportional constant. Or that number is also the unit rate if we have context. So with context, it would be the unit rate value. Okay. Notice, there is no additional information. It's just strictly, as we said, a multiplication division type of relationship. So, rather than saying it is divide, we could say multiplying by an improper fraction, or multiplying by a fraction, or multiplying by a mixed number or decimal. So we would be looking at strictly something equals a number times the other value. And going back to our graph, it's always y equals something times x. Going back to our table, how do we get y? We multiply x by the proportional constant. So these are the things that we would be looking for to make sure that a relationship is proportional. And that's what we're going to do with our next few examples. So we've got a couple of tables here, and it wants us to determine whether they're proportional between x and y or they aren't. Remember, the clue is there should be a proportional constant. If I look at each of these values, there should be a constant number that I can multiply x by to get y. In this one, if I look at all of these values, well, if I multiply 1/2 by 2, I'm going to get 1. Well, if I multiply by 2 here, I need to be able to multiply by 2 all the way through. So let's see if everything I do is a multiplication of 2, or our proportional constant. 3 times 2, 6, yes. 5 times 2, 10, yes. 10 times 2, 20, yes. That means that this is definitely a yes. It is proportional. We do have a proportional constant. My other one, if I look at that and I say, okay, I'm starting with 1. Well, for 1 to become 6, I would need to multiply by 6. Yes? Hey. Well, 1 times 6 is 6. 0 times 6 is 0. Uh-oh. 2 times 6 is 7. Nope, that doesn't work. And 3 times 6 definitely doesn't work either. If we look at this, what it looks like is it's an addition of 1 each time. That's not going to work. Remember, it can't be an addition that isn't a repeated multiplication. So when we look at this, does 6 work here? No. No. So if only works on half of them, is this a proportional relationship? We write that it is not proportional, because everything should be multiplying by 6. Quick way to discover with your tables. Another way would be to put all of your values in fraction form, just like we did on the example of how would you know? Each of these, if I put them in fraction form, now that one's going to be kind of funny, but look at this. 6/3, 10/5, 20 halves, or 20 tens, sorry, 20 tens. Funny thing is, every one of those simplify to be 2, my proportional constant. If I try doing that over here, well, 6 ones are 6. I can't really write 0 zeros because that doesn't work. But 7 halves and 8/3, that's 6. That's 3 1/2. And that is 2 2/3. Those things are definitely not equal. They wouldn't be multiplying by the same value. So just another way of checking to see whether a table is proportional or not. Of course, you could always graph it, but that would be then taking us into another kind of, is it proportional or isn't it? Speaking of graphs, we want to talk about whether or not these would be proportional. So it does ask us if it is proportional to write an equation. Now, as you look at these 2 graphs, I hope that you can see that very obvious that B could not possibly be proportional. This would be an absolute no. 1, it isn't a straight line. Although it does contain the origin, it is not a straight line. So for us right now, do we have an equation? We're going to say no. Oh, later on, as you move up higher into other grade levels, you will discover there is an equation for that, but it's not a proportional equation. And you'll learn about those later on in your math career. This one, proportional? Yeah, this one is proportional. First off, straight line, up, has the origin. So we would say that, yes, this one is proportional. How do I write an equation? Well, as I look here, oh, I've got a 1 right there. 1 and 6. When I put in a table that my x value is 1 and my y value is 6, let's see if that other pattern follows. When x was 2, y was 12. Oh, they have a multiplication relationship, meaning they have a constant of proportionality. That constant of proportionality is 2. Remember, to write an equation, I start out with y. What does it equal? Y equals something happening to x. Well, what happened to x? I multiplied by 2. So I'm going to write that y equals 2x. Pretty simple? Yes? No? Yes, no. What?
Your concept of proportionality value is 6, not 2.
Oh, my constant, oh, I messed up. Ah! Oh dear. Woo, how embarrassing. Woo! Yes, people do mess up. Teachers do mess up, especially on video. Sorry, it's 6. I don't know what I was doing there. Oh my gosh. I was going the other way around. I was going vertically instead of horizontally. Well, that just goes to show you how easy it is to mess up. Make sure that it's the horizontal rather than the vertical, because yes, 1 times 2 and 6 times 2. Oops, my bad. So, we fixed that. We're good. Okay, and you're probably sitting there laughing going, guess what? That's okay. I could have said, yeah, I planned it that way. I didn't. You know, stuff happens. So, and it's pretty funny when it's on camera. So there's the blooper reel, so to speak. Alrighty, let's take a look at 2 more graphs. As I look at these 2 graphs, first of all, looking at C, well, it is in a straight line, and that's what I want. The only problem, look at this. It doesn't start at the origin. The origin is not there. And because the origin is not there, I'm going to say that this is a big, huge no. For us right now, for an equation, we're going to also write no. For now. Later on, you'll find out that there is an equation for that. It's just not proportional. And what we're doing is we're writing proportional equations. Our next one, D. Ooh, this contains all 4 quadrants. But remember the example that we drew. Hey, as long as it's a straight line, it is, and it goes through the origin, it does, then we would say that this one is proportional. How to figure out what to do with this? Well, this one is kind of interesting because on our graph, we just see 3, 6, 9, -3, -6, -9, and 3, 6, and 9, and -3, and -6, -9. What's nice about this is our x values actually have a place for 1 and 2 and 4 and 5 and 7 and 8. Although that doesn't happen on our y values. But remember, if we look at where x is 1, where is y? Y is 3. So where x is 1, y is 3. So if I put that in a table where, sorry, this is kind of, whoops, messing up. If I put this in a table where x is 1 and y is 3, right there, I have my constant of proportionality. It's going to multiply by 3. I even could go over here, reset because it moved, and say, oh look, 2 is 6 and 3 is 9. So 2 times 3 is 6, 3 times 3 is 9. It works out. So my equation is going to be y is equal to what I'm multiplying by, 3. What is 3 multiplying by? It's multiplying by all my x values. So y equals 3x. This one's correct. All right, no mess up on this one. And there you have a proportional one with all 4 quadrants, and back here, a proportional one that is strictly in quadrant 1. As we look at these, definitely not, first of all, it's not a straight line. Definitely not, because even though it's a straight line, it would need to drop down to the origin, and it does not do that. So, graphs, straight line, going through the origin or starting at the origin. All right, equations. Now equations, we said, they need to be y equals some number times x. All right, we're just going to decide if that is proportional, yes or no. Well, as we look at our first one, it literally says y equals 2x. Y equals, that's what we want, 2x. Yeah, 2 is our constant of proportionality. And so in this case, we'd say proportional. Oh yeah, this one definitely is. B, wait a minute, it's got divide. Uh-oh. But, oh, division and multiplication are inverses of each other. I can actually write divide by 3 as times its reciprocal. So, remember, dividing by 3 is the same as multiplying by 1/3. We've been talking about that all along with fractions. When you can't divide, you can multiply the reciprocal. So that means I could rewrite this problem as y equals 1/3 times x. Oh, hey, now that looks kind of like that. And my 1/3 then is my constant of proportionality. And yes, it's going to kind of go over into the other box, but that's okay. So, is this one proportional? Yes, this one is proportional. My next one says y equals 2x plus 1. Wait a minute. 2x plus 1? That's not proportional. The thing about this one is the moment we have any extra stuff, that moves it off of being proportional. It won't go through the origin. If I replace x with 0, y wouldn't be 0. I don't have a proportional relationship here. This is a no. I can't be proportional because that can't be any value added on. We cannot have any additional values. That shifts everything. And that wouldn't be a strict multiplication or division relationship. It would now be 2 processes, 2 operations, not proportional. Proportional is just 1, multiplication. Okay? So, our next thing is context. And when you're looking at context, well, sometimes you might think, wow, there's a lot of stuff in there for context. But remember, we've already discussed how do you write equations from context. So as we look at these 4, if we can write an equation, then we can decide yes or no. So if I look at A and B, they're both about rental plans. Rental plan A says a $30 initial one-time rental fee plus $45 per hour. All right, so right here I have $45 per hour. I know that's a unit rate. When I have a unit rate, I can write it as 45 times, let's just go hours. But also, look what else was in this. It had the word plus. That is being added on to something. What's it being added on to? It's being added on to $30. Wait a minute. I now have addition and multiplication. If I have addition and multiplication, is that proportional? Oh, no. This cannot be proportional, and the reason it can't be proportional is because I have something other than just a multiplication. Look at rental plan B. Rental plan B says $50 per hour with no initial one-time rental fee. So right there, I have $50 per hour. That is a unit rate. Remember, my unit rate is my proportional constant. I could write that as 50 times H, and this says with no initial rental fee. That means I'm not going to add anything on. So if I'm not going to add anything on, hey, we're good to go. It's just going to be a multiplication relationship. So for proportional, this one we would say it's a definite yes. Look for clues. The moment that had plus, no longer proportional. So let's take a look at these about Allie and Barb filling up their swimming pools. Allie and Barb are both filling swimming pools at a constant rate of 2 gallons every half minute. Allie's pool started with 6 gallons of water in it. Okay, let's kind of think about that. We do have the words constant rate. So the fact that we see right here a constant rate, that gives you a hint that 1, there's a unit rate, and 2, it's constant, so there will be a constant of proportionality. Now this one is 2 gallons every half minute. If we were to look for the unit rate, we would need it for 1 minute, which would be 4 gallons every minute, or 4 gallons per minute. But wait, it tells us Allie's pool started with 6 gallons of water in it. Uh-oh. That means she had 6 gallons of water sitting in her pool, whether it was from rain or melted snow or last season and they didn't clean it out, whatever. But when she had 6 gallons of water in her pool, that means she had that in additional. That was an additional amount. And so when she's got an additional amount in there, is that proportional? Oh, heavens no. But if we look at Barb's pool, same information down there, and it goes to the point where it says that Barb's pool was empty. That means there's no extras. And if there are no extras, proportional, yes. So we have talked now about equations, context, tables, and graphs. All the different ways and means of deciding whether something is proportional or not. Most of these are very visual. Some of them you actually have to read and look for clues, but it is pretty easy to decide if something is proportional or not. So, if you have any questions, make sure you contact your teachers, ask them for some extras, maybe go back, pause the video, though don't pause it too long on the one where I made the mistake. Bye now.